Folks, in our next 6C7 practice problems, we're going to take a look at the carbonate ion as an example. The carbonate ion is CO3 2-. This is the first one we're doing here with the valence shell electron pair repulsion theory that is charged. So we'll talk about how to do that. So we're working with CO3 2-, and we want to figure out what the name of the shape is, and we want to look at some of the properties or characteristics of this molecule. So let's see if we can figure out its shape. First thing, we have to draw it. So in order to draw it, I have to figure out the total number of electrons. So carbon is in family 4. This molecule has 1 carbon in it with 4 electrons. There are 3 oxygens, each with 6 electrons for 18. And this is a molecule that has acquired a 2- charge. It is a molecule because we have carbons with oxygens. Those are nonmetals. But this is called a polyatomic ion. It is an ion that started as a molecule. So we had a molecule CO3 2-, and it is charged. We'll figure out how it got its charge. So we've got 1 carbon with 4, 3 oxygens with 6 for 18. It's 2-, so this molecule's picked up 2 electrons. So we have to add those 2 electrons on. 4 and 18 and 2 is 24 electrons on the molecule. Who's going to be our central atom? Our central atom is going to be the carbon. It needs 4 bonds. Oxygens have 6. They only need 2 bonds to get 8. Carbon starts with 4, has 4. It needs to use all 4 in order to get 8. So carbon is my central atom. I'm going to build the molecule around carbon, so I'll now surround carbon with 8 electrons. So here's our carbon with 8 electrons. Wherever there is a lone pair, I can attach the oxygen. So I can put an oxygen here, here, here. It doesn't matter, anywhere around there. So I'm going to go ahead and attach the oxygens, and then I'm going to surround them with 8 as well. So let's take a look up here. I've attached the oxygens, and I've surrounded them with 8 as well, and it's 2-. That 2- means 2 of these electrons were grabbed by this molecule from something. And in fact, they grabbed them from hydrogens. At one time, this molecule had 2 hydrogens, 1 there and maybe 1 there. These hydrogens were on the molecule at one time. Remember, oxygen is very strong. Acids are molecules that have hydrogen attached to it, and then the hydrogen breaks off after oxygen rips its electron from it. So here's a hydrogen bonded to the oxygen. Oxygen grabs hydrogen's electron and kicks that hydrogen off as H+, the hydrogen ion. This oxygen was bonded to a hydrogen, and it ripped hydrogen's electron off and kicked that hydrogen off as H+ as well. And now this electron belonged to that hydrogen, this electron belonged to that hydrogen, and the hydrogen ions kicked off, and now the molecule has acquired a charge. It's 2-. The CO3 2- is what is left of a molecule that started off as an acid. Molecules that kick off hydrogen ions are acid. So now, that's where the 2- came from. But let's take a look at how many total electrons are on this molecule. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We're only allowed 24, and it has 26. So we can't just go to step 4 and draw the Lewis structure by replacing shared pairs with lines, because we have too many electrons. So I have to erase 2. I can erase 2 from any atom that is attached to another atom that has 2 electrons that are free to place in the bond. So I could erase this pair, and I could or this electron and this electron. I can erase really any pair from here, just not the bonded pair. So I could erase that pair, 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 that pair. I can erase any of those pairs because carbon has that pair that it could put into the bond between any of its atoms. Likewise, I can erase this pair because any of these oxygens have a pair that I can put in to replace it. So here we go. Let's get rid of this pair right here. I'm getting rid of that pair. And I can replace that pair with any pair. I could put this pair into the pond right here. Any of these pairs will go in. So I can take this pair right here and move it into the bond. Carbon lost the 2. I erased the 2 from carbon. So I now need to add 2 more into some. I need to move 2 into the bond to replace the ones I erased. I'm fixing it. So now carbon has 1, 2, 3, 4, 5, 6, 7, 8 around it. It has 8 around it again after I erased the original 2. The oxygens whose electrons I moved in still has 8 around it. 1, 2, 3, 4, 5, 6, 7, 8. So I haven't upset anything. But now I'm down to 24 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've met that 24 quota. The fact that I could have moved this pair in or this pair in instead of that pair means that there could have been a double bond between this carbon and this oxygen, this carbon and this oxygen, or the carbon and the oxygen on the left. So the double bond could have gone to the right, to the bottom, or to the left. Any of those places would work. Where the double bond could have been anywhere makes this molecule have something called resonance. Resonance means that the double bond could be anywhere. When something resonates, it vibrates. What that means is this. This oxygen could actually pull that pair back. And then the carbon could pull that pair in from this oxygen, making the double bond there. This oxygen could pull its electrons back. And then the carbon could pull this pair in, making the double bond there. Where the double bond is everywhere, and this happens multiple times, some say thousands of times a second, electrons are getting pulled in and out of the bonds because electrons are in constant motion. Thus the term resonance. Resonance is when something's vibrating quickly. The double bond vibrates quickly between all the oxygens surrounding the carbon. So it is really everywhere, all at the same time. That's what resonance is. So for the purposes of this drawing, I now have the double bond back to the left. I have the total number of electrons I need, so I can proceed to the final step of drawing this, where I replace shared pairs with lines. So there's my double bond to the left. That's where I had the double bond, but it could have been to the bottom and to the right. Which one is it? It's actually in all of those spots at the same time. I've got my brackets around this molecule because remember, anytime you have something that is charged, that has more electrons or fewer electrons than it's supposed to, the brackets indicate that. Now we're ready to move on and determine the shape of this molecule. All right, so here's our Lewis structure. Now I need to count my total things around the carbon. Here's my carbon. How many things around it? How many atoms are bonded to it? 1, 2, 3. I count the atoms, not the bonds. So there's 3 atoms. How many lone pairs are on the carbon? There are none. So there are 3 total things surrounding my central atom A, which in this case is carbon. So in this box I put a 3. How many of those 3 things are atoms? The answer is 3 of them. B stands for how many bonded atoms? There are 3. So I'll put that right there in that square. How many of those 3 things are lone pairs? Well, if there's only 3 things and 3 of them are atoms, there are no lone pairs on this molecule. And we can see on the drawing that there are no lone pairs on the molecule. So we put a 0 there. And now what's my shape formula going to be? Shape formula is AB what? My B is 3. There are 3 bonded atoms. So on my shape formula, my bonded atoms are 3. My lone pairs on this atom are 0. So I could just write AB3, or I can put AB3E0. It means the same thing. AB3E0 is the same as just AB3. Now I'm ready to go to the shape sheet. I'm looking in the leftmost column for 3. Second column from the left should have a 3. Third column from the left should have a 0. So I'm going to go to my shape sheet. Here's the 3 on the left. I'm looking for the 3, 0 with the formula AB3, AB3E0, as it says right here. That's what I'm looking for, AB3E0. I'm looking for the 3, 3, 0. I've got it. I've got that. Now I can go to the shape sheet and see what the name is of this molecule. It is called trigonal or trigonal planar. So I write trigonal planar right here. What are the bond angles? We could probably figure this out without looking at the shape sheet. If I have three atoms, each pushing against each other equally, because remember that pair of electrons in all of those spots at essentially the same time, these are going to push each other in a plane. So if I take a plane, a circle's 360, if I divide it into three, the bond angle then should be 120. Each of those atoms are evenly distributed. If it wasn't evenly distributed, if there was a lone pair, then that 120 angle would close dramatically. Let's make sure we've got that right on our shape sheet. Trigonal planar, it is 120. There are no lone pairs. The atoms are symmetrically distributed about the central atom. So it is symmetrically shaped. So I'm going to put a little star right here. There are no lone pairs. These atoms are spread about evenly. In your drawing, it looks like it's T-shaped, but they would actually have an oxygen here, one down here, one over here, if it was drawn three-dimensionally, which it's not. Now, if it's symmetrical, we know that we have not met one of the qualifications for the molecule to be polar. For it to be a polar molecule, if you look back on your shape sheet, for it to be a polar molecule, it's polar if and only if it's asymmetrical. Well, the molecule we're looking at is symmetrical, so it can't be polar. It has to be nonpolar. It's nonpolar. But they do want the type of bonds here. But whether the molecule's nonpolar or polar here doesn't really apply, because a nonpolar molecule is saying that the bonds are nonpolar. Or the molecule doesn't have a dipole. That's correct. The molecule doesn't have partial charges. It doesn't have partial positives and partial negatives. Why? Well, because it's symmetrically shaped. But there's a much, much stronger force on this molecule. Folks, it doesn't matter whether this molecule is polar or nonpolar. This molecule has a full charge to it. This molecule is ionic. It's 2-. It's ionic. That is much stronger than if it was polar or nonpolar. So when there's a charge here, you can go to the polarity. It isn't polar. The molecule is fully ionic. Now, what would the type of bonds be? Well, we could look on the electronegativity table. The type of bonds here doesn't matter. First of all, it's symmetrical. So if there were polar bonds, they would cancel out. Secondly, it's ionic, so we don't care if the bonds are polar or not, but for the fun of it, let's go to the electronegativity table. Let's look them up. Oxygen's 3,5, carbon is 2,5. What does that mean? 3,5 minus 2,5 is 1,0. That would be a polar covalent bond, but it wouldn't matter because the polar covalent bonds, the little dipoles cancel out. Again, oxygen's 3,5, carbon's 2,5. The difference is 1,0. The bonds would be polar. If there was no charge, the bonds would be polar, but the little dipoles would cancel out, making the molecule nonpolar. But in this instance, since it's charged, the strongest force is ionic on this thing. This is not partially charged. This is fully charged. What state of matter would we expect this carbonate ion to be in since it's fully charged? The carbonate ion is going to be something that would exist as a crystal lattice. It would be a salt in solid form, assuming, of course, it wasn't dissolved in aqueous solution. So when it is an ion, when the molecule is a polyatomic ion, poly meaning many atoms, when it's charged, you don't really even have to answer if it's polar or nonpolar. It's ionic. We can still figure out if the molecule is symmetrical or asymmetrical. The type of bonds, again, don't really matter because it's fully charged. But if it wasn't fully charged, the polar bonds would have canceled out anyway. So that takes care of the carbonate ion. And then as our third example problem on our 6C7 example problems. And from here, we will now begin doing some of our own problems, filling out the sheet just like this. Good luck. And if you have any questions, don't hesitate to ask.